Okay, acids, bases, and buffers, the lab. Part A, we're making cabbage juice indicator. It's really neat. Cabbages, pink or purple cabbage, red cabbage, I guess they call it red, but it's really purple. Has natural organic compounds as part of the cabbage. It produces it on its own, which react to acids and bases and actually change colors. And there's several in there. When you combine them all together, you know, you combine colors, you get new colors, right? When you combine it all together, we can get a fantastic indicator for the pH. All right. Part A was to create that cabbage juice. I'm not going to do that. We already have it ready. Cabbage juice, we did this already beforehand, but essentially you take the cabbage, chop it up in little pieces, put it in a pot, put some water and boil it, all those juices come out, put it through some cheesecloth, which is a strainer essentially, and we get the juice. We collect the juice and cool it down. So there it is. We've done it already for you, cabbage juice indicator. And if you look at the cabbage juice indicator in its normal state, you can see it's kind of a purplish color. And I can hold it up here and you can see that. Kind of a purple color like that. Okay, we have 13 different solutions that we know already what the pH is. This comes from the chemistry lab, all the way from pH 1, which is down here, which is going to be very acidic. The next one's pH 2, and all the way along here to pH 12, and eventually all the way up here to pH 13. And we got them separated. pH 7 is neutral. Above 7, those are bases. Below 7 are acids. All right, so for part B, we're going to calibrate our cabbage juice. That is to say, what color does this cabbage juice change when you subject it to pH 1 or when you subject it to pH 2, and right on down the line so we can get a calibration. And to do that, we simply put about 3 milliliters of each known solution into a test tube. So let's see. Here's 1, 2, and you don't have to be terribly careful with this. We want about 3 milliliters. So there we go. And so our first test tube, you can see it down there, and it's just a clear solution, but that's going to have a low pH, pH of 1. And we've got our test tube labeled 1 to remind us of that. And I'm going to go right down the line and add 3 milliliters to each test tube. As I go down, I'm going to move these over so I don't forget where I'm at. That's a little trick, just to kind of keep track of things. Oops. Okay, so pH 2. Yeah, there's 1, 2. Each squirt is about a milliliter. Obviously not very careful measuring, but to create this calibration curve, it is good enough. One of the things about pH is when you just look at the solution you have, you cannot tell just by looking at it whether it's an acid or a base or whether it's neutral. You have to measure it somehow. And using an indicator like we're going to do here with the cabbage is a great way to measure it. And so, for example, you look at these 3 first solutions, and what I could do, I've changed my mind here. Well, let's see, 1, 2, 3. Now we're going to keep it just like this. If I put this in the back, there we go, nice white background. You can see, this one's clear, that one's clear. This one's got a slight yellow tint to it, but again, that doesn't mean anything as far as pH. It means absolutely nothing at all. Okay, so that's pH 1, 2, and 3. Here's the pH 4 solution. And add 1, 2, 3 milliliters there. pH 5. 6, pretty much clear solutions. 1, 2, 3. Of course, that's good when you're trying to look at the color after you add the indicator. When we add our cabbage juice, we expect it to change colors, and a good clear solution actually is beneficial. It's good to have. If it was already colored solution, that might make it kind of hard to see what color the cabbage juice changes when you add it. And so I'm kind of happy that they're all clear, truthfully. But out in nature, out in the world, yeah, these solutions could be any color at all. Again, color of the solution does not tell you whether it's an acid or a base, not on its own. All right, we're up to pH 8. Oops. Drop the cap. 1, 2, 3. pH 9. You see some of these bottles actually says pH 10 buffer. And a buffer is simply a solution that resists changes to pH. And part D of this lab will actually try to work with buffers a little bit and see that in action. Buffers are nice. Buffers in the body are pretty important because we don't want our own body pHs going really, really high or really, really low. We want to keep them in a nice range, and buffers will do that for us. All right, there's 11, 2 more to go. 12. And pH 13. Okay. So there it is. We've got our solutions all, move that so the camera can take a look at that. We've got our solutions all together there, and there's nothing to see yet. They all look more or less clear. Some of them have a slight tinge. However, when you add our cabbage juice, which will be the indicator, hopefully they'll get different colors as we add it. Let's look at the protocol here. It says add about 2 to 3 milliliters of the cabbage juice. So, same kind of thing. As we add each one, we'll find what's happening. And I wanted to do, I have a glove. I'm going to get a glove real quickly here, just to make it a little easier to mix. Put the finger over it that way and mix each test tube. Okay, here we go. Cabbage indicator. Now this time, of course, we're going to get the same in the same bottle each time. I'm going to just see if I can give a big squirt, maybe make things a little faster. All right. Hey, look at that. I added purple, and clearly it didn't stay purple. And actually, that mixed pretty good on its own. I was going to take it, and with my gloved hand, and just invert it a couple times. That's a good way to mix it. But it looks like if I kind of squirt it in there, it mixes pretty well on its own. So pH 1, wow, I got this nice dark red color. Let's try pH 2. Not quite as acidic. Put a great big squirt in here. Purple to start with. We add it. All right, it's reddish, but not as much as the first one. And so we're already seeing, if I had a pH 1 versus a pH 2, I could tell the difference using cabbage juice. Pretty cool. Let's try the pH 3. This is still acidic. Remember, everything below 7 is an acid. Everything above 7 is a base. All right, so there it is. pH 3, more of a nice pink color. Very pretty, I think. Let's go to pH 4. Our cabbage juice is working really well here. All right, pH 4. Now we got more of a purple. In fact, it didn't really change much color. Purple in, purple out. Kind of makes me wonder if cabbage juice itself doesn't have a pH of about 4. I don't know that for sure. I'm just kind of thinking out loud here. That might be true. pH 5, so a little less acidic again. And a little darker purple. Can't tell those apart as easily, but you still can. It's a little different shade of the color, which is really nice. 6. So this is our last acidic solution. And it's darker purple yet, isn't it? That one's pretty close to the 5, but again, perhaps could tell that apart. pH 7, now that's neutral, right in the middle, so it's neither an acid nor a base. Neutral solution. And, oh wow, we got more of a bluish color. Blue-purple, I'm not sure what to call that, but clearly we can see a difference there. Isn't that pretty though? It goes from this red all the way through purple, now we're hitting blues. All right, pH 8. So now we're up here into the bases. Basic solution. And of course our blood is just ever so slightly basic. That's pH 8 right there. pH 7 was the blue, pH 8's actually turned almost like an aqua, got a bit of a green tint to it. And our blood is pH 7.2, 7.4, somewhere kind of in between there. So if, I'm not going to do that, but if I tested my own blood, I would expect it to be somewhere around that color if I use cabbage juice as an indicator. All right, here we go, pH 9. Nice. We're getting a real nice green color there. pH 10. Cabbage juice. Oh, we're back to a bluish, although it's a different kind of blue than down here, so again, I can still tell that apart. pH 11, now we're getting a little higher there on the base side. Greenish, that's kind of interesting. It went from green to blue and then back to green. pH 12. Oh, there's more of a yellow to almost green color. And then finally, 13, the highest pH here that we have. So, highly basic. And it's that same yellow-green. Those are kind of hard to tell apart. So the cabbage juice is not going to differentiate on that real high pH 12, pH 13. But just about everything else, I think you can pretty easily tell what pH solution you have. And remember, we added the same amount of cabbage juice each time, and yet we got all these different colors because the initial solution was at a different pH. Now what's nice is this is our calibration curve. We can use this to check anything else. Add the cabbage juice, see what color it turns, line it up, match the color, and you can find out, or you can tell exactly what the pH of any solution is. And that's what we'll be doing in parts C and D of this lab. Okay, part C. Now we're going to test different household items to see what their pH is. Are they acids? Are they strong acids, right? Really, are they really low on the pH? Or are they bases? Are they really high on the pH scale? Remember, 7 is the dividing line. 7 is neutral. And so we have, just to go through which items we'll be testing, vinegar, Dr. Pepper, coffee, black coffee, baking soda, pure baking soda, milk of magnesia from the pharmacy, ammonia cleaner, some Easy Off cleaner, oven cleaner there, and then tap water, water right out of the tap, versus deionized water, all right, where we've purified that a bit. So, I don't know, acids, bases, we're going to check it. We're going to do it 3 different ways. We're going to check it using our cabbage juice. We're going to check it using indicator paper and then with a pH meter. So let me show you this first. This is the indicator paper. They make this where it comes in a roll and you just tear it off like this. Okay. And on this paper, it's kind of orangish to start with. There are chemicals. I'm going to go ahead and just put a little piece, I think, in front of each one of these. I think that might be a good way to do this. There are chemicals that they've identified that change color, just like our cabbage juice changed color as well. And so I'm just putting a little piece of paper in front of each one. We'll test each one of them this way. Baking soda, milk of magnesia, ammonia, easy off, tap water, and GI water. Okay. And when we test each one, it'll change colors, and let me just kind of hold this up there so the camera can zoom in on it. Right on the package, it shows the colors that it changes for each pH. And you see we've got kind of a reddish down there at 0 and 1, then it goes through orange and yellow, green, finally turns into these dark blues at high pHs. Okay, so universal pH paper. The way to correctly use this is to put a little drop of whatever sample you're testing on the paper. All right. Some people, when you first start chemistry, you think, hey, I'll take it and I'll dip it in my solution. No, that's not the right way to do that because you can contaminate your solution with whatever chemicals are on that paper. All right, so we've got our vinegar and we've already got it poured out into this little bottle, just make it easy. And so I'm not even going to use this dropper to squeeze it. I'm just getting a little drop that's hanging on, and I'm going to just touch it right there on the paper. All right, and you can, I'll let the camera kind of zoom in on it. Didn't change too much color, a little bit of red around the outside, and in the middle of the drop, kind of stained orangish. All right, and so if I was to line that up, I'll let you make the call as far as what pH you want to call that, and you can record it on your data sheet. All right, same thing here. Dr. Pepper. We'll just give it a little drop and let it touch on the paper. Very similar result. Very similar. Black coffee. I hope you can see that's a little bit of a different result as far as the color that it's changing. And it's mostly on the inside, that's what you want to look at, the color. Like this has got a color on the outside as it's going into it, but it's that inside color that you want to look at. Here's some baking soda. Of course, baking soda is actually a powder, and so to do this, we're going to have to put a little water on this and stir it up. Do we have a deionized water around here? Okay, I'm going to go get a wash bottle.
Is there one, Dr. Pianta?
Oh,
is there
good,
one?
good,
Yeah.
All right, so what I've done, and it's just because I didn't prepare ahead of time. I probably should have used a test tube, but I went ahead and, you know what, actually I can use a test tube over here. This is one, 2, 3, 4. This is the 4th sample. I'm going to do it right here in this test tube. Here's number 4 for the baking soda. I'm going to get a little bit in this, and then we'll add some water to it. This is deionized water, and so, because we can't test a solid very easily, can we? We need to drop it onto the paper, all right? And so, shake this up so it dissolves most of the way, and then let's go ahead and I'll just use this as my dropper. We want to get a dropper on that paper there. Didn't get much today. There we go. Okay. And so, there you go. There's the baking soda. Okay, moving right along, milk of magnesia. We have that again already set to go. Let's open up milk of magnesia and get this out of the way. Whoops. This is kind of thicker stuff. There we go. Put this over here so you can get the color for that milk of magnesia. And that's a little milky, you got a little white, so you kind of have to look past that when you're trying to figure out the color. Ammonia. So this is right here. Ammonia. Put it down. Wow, look at that. In fact, the fumes from ammonia are actually surrounding that paper there, and it's not just the liquid, but the fumes are making it change color, which is really a neat effect. Very good. So there's ammonia. All right, working down the line here. Next we have Easy Off Oven Cleaner. And of course this is a spray. So what I'm going to do is I'm just going to spray a little bit right here into the tray. Just like that. And then we'll be able to touch a little bit onto the paper. And get a sense of the pH for that guy. Okay, tap water. Okay. Oops. And finally, DI water, deionized water, where we've removed ions and purified it a little bit. That's what that looks like. And there's its result. And if nothing else, you can clearly see deionized water versus tap water. It's not the same, is it? That tap water is clearly not neutral pH. Okay, so we have tested the pH. I haven't told you the number. That's up to you to figure out what you want to call it. But we've tested all the pHs using universal pH paper. Next, we could do the same thing using our cabbage juice indicator. And so we'll use our test tubes to do that. And from part B, you'll remember that was our indicators that we created. So I'm going to just kind of move this along as we go. And we'll do the same thing. We'll test them as we go along. So here is vinegar. About 3 milliliters, just like what we did before. 2, 3. Vinegar. And my cabbage juice. I'm going to go grab that. There we go. And we put a squirt of cabbage juice into it. All right. And so, if that's the cabbage juice in the vinegar, mix a little bit, you can line that up and you can say, well, I think it's closest to whichever color. You know, obviously it's down here. And so, again, you can make that call. It's probably going to be somewhere in this range, I think. And remember, these are the actual pHs, so pH 1, pH 2, pH 3, pH 4. And you can really just match it up. And hopefully you're going to get about the same result that you got when we were using the indicator paper. Whatever the number you want to call each one to be. So, there's our vinegar, and we'll keep trying the same thing for each of our household items. So Dr. Pepper, let's try that one next. 1. And this, of course, has a little bit of a color to it, and that might interfere a little bit with seeing the color clearly, because it starts off not clear, it starts off brown. That's okay, do your best. Squirt in the cabbage juice. And that brown color is quite clearly interfering with the cabbage juice color a little bit, but nevertheless, it didn't change it a whole lot. I would think if it was a strong color, it might have changed it more. So that one's going to be a little harder to call, but it is what it is. Let's keep on moving along. Coffee. Good thing we have other ways to measure pH as well, and that's part of what we're trying to show you in this lab. pH of coffee. A coffee, of course, is going to be a brownish color as well. So there you go, 3 milliliters of coffee, black coffee. So we haven't added creamer or sugar or such, just the coffee. And then here comes the cabbage juice. All right, not much of a change there. Give it a quick mix, just like that. So sample number 3, black coffee, just like that. Sample number 4, the baking soda. That's what we'll do next. This is where we need to add a little more and put some water in there. So I'm going to add just a little more. We already started this before. Just going to do a little more. There's the solid. We'll squirt a little more water in there. The solid's sitting on the bottom. Let's see if I can mix it up a little bit. Okay, and let's go ahead and add some cabbage juice to that. Oh, look at that. Definitely a nice different color. So let me give that a quick mix. And hold it up, and again, figure out what color you want to call that at with the cabbage juice. Okay. And I'll set these all out at the end here as well, kind of as a summary. Let's keep on moving along. Milk of magnesia is sample number 5. So of course this is kind of creamy and milky to start with. Luckily, it's a white milky though, right? So it might not interfere too much with the color. Milk of magnesia. Cabbage juice. That looks interesting. It's kind of neat. You can see how things don't necessarily mix right away, depending on what the sample is. But we'll shake that up there. I'm getting this frosty green. Of course, the frostiness is from the white milky part of the milk of magnesia. The color is what you want to try to match up though, and figure out. So there we go. Number 6 is the ammonia. Of that. 1, 2, 3. Cabbage juice. Quick mix, and there you go. Now hold it up in front of the cabbage juices again, maybe right next to it. I'm not sure which is best. And now our Easy Off. I'm not sure the easiest way to get Easy Off. I wonder if I could spray it right in the tube. I haven't tried this ahead of time, but we're going to give it a shot. I'm going to see if I can just kind of spray it right in here. Yeah, more or less. Got this. Try to maybe push it down a little bit. This is going to be the hardest one. Actually, what might be even easier is to mix it directly in here. We might do it both ways. Okay, let's squirt some cabbage juice in there and see. All right, yeah, that definitely worked. You can still see what it is, and I'm gonna. Actually, that worked fine. I don't think I need to do it in the tray as well. Not going to be so easy to mix it, but there you go. There's the result. You can see the solution on the bottom, and again, just trying to hold it up here. So it had some initial color to it as well, but I think that very bottom you can see is pretty yellow in the color. All right, and the last two, our tap water. One, 2, 3. Cabbage juice. Oops, drop the cap again. All right. So there's our tap water. Just hold that right next to it there. Versus our deionized water that's been purified a bit. Last two, 3 milliliters. cabbage juice indicator. Okay. And again, our cabbage juice is showing us there's clearly a difference between tap water and deionized water. So there we go. Our 6 different samples with our tap water and our DI water all laid out for you there. Okay, the last part of this, part C, we will test the pH of some of these household items, but this time using a meter, a pH meter. The meter we have here is a battery-operated portable meter, and it can actually measure both pH and millivolts, so we got to make sure we're in the right mode. This is the actual probe, the pH probe, and it's got a solution on the inside, and it's stored here in a storage solution because we don't want this bottom part to dry out. The bottom part is a glass bulb down there that is sensitive to the pH of solutions. It's actually very fragile as well, so they put a nice plastic kind of cage around it to help protect it. Okay, and so we take this and we plug it into the side of the meter, which has just got a simple BNC connector. Pop it in there like that, and we can turn it on. And so hopefully that will show up well enough on the camera. Of course, I don't have it in a solution right now, but it's got 7.97 that it's showing, and it's 77 degrees Fahrenheit. pH does change a little bit with temperature. Anyway, the first thing to do is to calibrate it, just like how we need to calibrate our cabbage juice to see what colors correspond to what pHs. We want to make sure that a pH 4 solution, for example, really measures a pH 4 here on the screen. So we're going to calibrate it. Every time you put this probe into a new solution, you should rinse it off with a little DI water. We'll make sure that we don't contaminate from one solution to the next. So we've got that there, and we'll go ahead and we'll open up pH 4 solution and we'll put it in. I like to give it just a little swirl just to make sure that it's well contacting with the bulb. And then over here, it's already measuring 4.01, which is really good. It's fairly well calibrated, but if I hold down the calibration button, it goes into calibrate mode. It thinks about the solution that it's in here for a second. I got to hit it again. I think it was doing it. I should have been just more patient. All right, so it thinks about it. And it says, all right, saved. SA means saved, and it's ended. So it's well calibrated. It's reading, again, 3.99 in this case, or 4 for the pH 4 solution. So that's perfect. It's well calibrated at that end. And you can calibrate all the way through to other solutions as well. So I've got a pH 7 solution, and we could do the same thing. Make sure it's calibrated for that. Put that in, swirl it a little bit, and see what it's measuring. Well, it's close. It's not quite 7, it's 6.9, so we're going to do the same thing. Hold down the calibrate button and give it a chance to calibrate at pH 7. There we go, it's saved. So now it's properly reading 7 for that solution. Let's take it off, we'll rinse it off, and we'll do the one last calibration solution, which is up at 10. Close the 7. There's our 10 solution. Put that in, and it's reading 9.96, pretty darn close, but we might as well go ahead and calibrate that as well. So calibrate, give a chance to think about that, and there we go, saved, and now it's reading 10. All right, so this meter is properly calibrated at 3 different points. 4, 7, and 10 are all reading correctly, so we have confidence now that when we put it into a new solution, it's going to properly read the pH of that new solution. This is just the same as, you know, like the old-fashioned scales. When you step on them, and it tells you the weight. Well, before you actually step on it, you turn the little dial on the side to make sure it reads 0 and nothing's on it. Or you tear the balance right in the balance room when you're in the chem lab. Same idea here. We've now calibrated it. Okay, so we're ready to use this now to measure our solutions, our household. And the instructions say to pick one that's going to be a high pH and measure it, a low pH, a neutral-ish pH, and then, hey, my choice of whatever I want. So let's come back over here to our cabbage juice results. And we'll go ahead and pick out a sample for each one like that. And so the low pHs, remember pH 1 or 2 had these kind of colors. Looked like sample number 1 was that, and sample number 1 was vinegar. All right, so I'm going to actually choose vinegar for my low pH. I'll go ahead and pour some into the beaker here for low pH. Okay, and that's the one that we will measure. All right. The high pH, let's see. The high pHs up here are 12 and 13. All right, these are the greenish and the yellows. So if I look over here, all right, sample number 6 was pretty yellowish and green, and sample number 6 was the ammonia. All right, so I'll use that for my high pH sample. Pour some into that beaker. Very good. The neutral pH, according to my cabbage juice, here's 7. There we go. Here's 7. Kind of got that bluish color, so that purple to blue to green, kind of in that transition region. Well, I mean, I could do one of the waters. I could do this one, which is number 4 if I want. Oh, that might be a little hot. Let's go with one of the waters. That looks pretty good. So, DI water, perfect. Neutral pH. Go ahead and pour that in. And then finally, my 4th sample, whatever I want. My choice. Let's try, you know what? Let's try coffee. Because coffee was tan, a little hard to tell the color of because it already had a color. So this way, the meter might work a little bit better to tell us the pH of that coffee. All right, so I've got my 4 different samples, low, high, neutral, and choice. Let's go ahead and use the meter now on each one of these to find out the pH according to the meter. As usual, I take my DI water and I rinse off my probe ahead of time. I don't contaminate the samples. And we'll put it in just from order. Well, the high one's my first beaker, so we'll do that one first. The high pH, put it in, swirl it around a little bit, and you can see what the meter's reading. All right. I'm going to rinse that one off now. And let's try the next beaker, my low pH sample, which I just got. Here we go, swirl it just a little, make sure it's in contact. And there's the low pH sample. I want you to read that and write that number down. Okay, very good. Rinse off the probe. Shake off the water. The neutral pH. Swirl that around. It's not stabilizing. The neutral-ish pH wasn't quite so neutral, apparently. Well, there you go. That's according to the meter. There it is. And finally, the coffee. All right, the brown one. Mix that up. And there's the coffee one. All right, so that is how you use a pH meter to measure the pH of samples. Part D, measuring buffers. Now, buffers are solutions that actually resist changing to pH. And what we mean by that is if you had any normal solution and I added some acid to it, like hydrochloric acid, well, I would expect the pH to go down because acids have low pHs. And if I take my original solution, add some acid to it, well, I expect that pH to go down. I'm adding acid to it. Acids are low. If I added a base, like sodium hydroxide, I would expect the pH to go up when I add it. Right? And so normal solutions are going to change when you add a strong acid or a strong base to it. Right? And because there's strong acids and strong bases, it doesn't take a whole lot. A couple drops are all it takes. Buffers have a neat property that they resist that. When I add a couple drops, say, of a strong acid to a buffer solution, it might drop a little bit, but just barely. It's not going to go way, way, way down. It might just just a little bit move, or if I add a strong base, it might go up, but just a little bit. It resists changing. It's a very important chemical system. And as I mentioned before, it's in the body. Our blood is buffered. Most of our body fluids are buffered because we don't want these wild swings of pHs in our body. So what we've got here is 4 different solutions that we'll test and compare how well are they working as a buffer. All right? DI water. I don't know. Will it work as a buffer? We'll find out. Sodium chloride, so table salt in water. Is that a buffer? Now here, a formic acid buffer. So this definitely is a buffer. It's a low pH one because it's actually, well, formic acid, it depends on its pKa. That's something that is beyond what we're going to talk about in this lab. And here's a high pH one, sodium carbonate buffer. So different buffers made from different chemicals. A buffer chemically is a weak acid and its conjugate base at the same time in solution. But again, that's beyond what we're going to investigate in this lab. All right, so 4 things to test. Let's just go ahead and set up our test tubes initially here. So we're going to take about 10 milliliters of each one, and it doesn't really matter too much. I think I'm going to use the DI water to initially, so I overshot that. This is just water, so I can pour that down the sink. All right, that's about 10 milliliters. The rest of them, I think I'm just going to need to eyeball it. It's not critical that we get exactly 10 milliliters. But on these large test tubes, okay, that's about 10 milliliters. Now that I know about what it is, on the other ones I'm just going to go right ahead and pour them right in. And actually, we're going to do this twice, so I'm going to just duplicate it each time here. So here's number 1, again, the DI water. I'm going to just go ahead and pour them all out right from the start here, so we'll be ready to go for both parts. All right, there's water, 10 milliliters, twice, 2 different test tubes. Here's my sodium chloride solution. Again, I'm just going to eyeball it. I know about what volume that is, so 10 milliliters is about right there, here, and in my second set of test tubes as well. Okay. The third one is my low pH buffer, the formic acid buffer. And once you know, they put it in a wide mouth bottle here. I don't know if I want to try pouring it out of there. I'd probably make a big mess. So let me just squirt it in instead. That's about done. Do it over here as well. And finally, my last solution that we'll test is the high pH carbonate, sodium carbonate buffer. 10 milliliters. Okay. And here. Sometimes measuring is critical, sometimes it's not. Depends if you're doing a quantitative experiment or a qualitative experiment. This is a qualitative one where we're just trying to see the quality of it. Does it go up or down pH? We're not trying to measure it super carefully. So, all right, so I'll set the second set aside. Here we'll work with the first step. All right. First, let's check what the pH is, and we'll do that using our cabbage indicators again. So there's our 1 through 13, and I need my cabbage juice, which I put down somewhere.
I put it in up there.
What did I do with that? Okay. Let's put a squirt of cabbage juice in each one of these now to see what we're starting at for each one of these buffers. So here is the DI water. All right, and again, you can match it up with the color. Here is the sodium chloride, the salt water solution. Looks just about the same, doesn't it? Here is the low pH buffer. Sure enough, that's a lower pH, right? That pink type color. And here is the high pH buffer. Yep, higher pH, the greenish color up there. All right, so we've got our indicator in each one. Next, we'll go ahead and add our strong acid to see, does it cause a large change in pH? And our strong acid is hydrochloric acid. Strong acid, this is a 0.1 molar solution of it. We're going to go ahead and add 5 drops each time to see if it changes it. So let me just make sure that these are well mixed first. And 5 drops each time. So here we go. First, the water, the DI water, 5 drops. 1, 2, 3, 4, 5. And you can see that's kind of neat before it's mixed in there. But if I mix it there, we definitely had a color change. And now you can see what the new pH is by matching it up to the calibrated cabbage juice over there. Let's do the same thing to our salt water. Let's see how it responds to adding a strong acid. Let me get my dropper full. Our initial one is that purple color. Here's 5 drops of my strong acid. 1, 2, 3, 4, 5. Okay. And we'll go ahead and mix it. And there's the 5 drops of that in the salt water. Let's compare that to my low pH buffer. Of course, this is already a low pH, just like my acid is. So we're adding an acid to an acid, basically, the solution here. 1, 2, 3, 4, 5. Again, we're looking, did it change color? And you can see, I think, hopefully that compared to these, where before I mixed it, you saw a difference in that top layer versus the bottom layer. Here, there may be a little bit of a difference up there, but not a whole lot. Let me just go ahead and mix it anyway. Doesn't look like a whole lot happened to that buffer, where these had definitely changed. In fact, look at now, they're all just about the same. They're all definitely acidic. Adding a couple drops of this stuff made a big impact. What about our high pH buffer? Let's try that one. So this one's up there in the base region. Let's go ahead and add our acid, 5 drops. 1, 2, 3, 4, 5. Okay, and again, it's kind of neat. At the very top, you're picking out just a little bit. Let's go ahead and mix it like that. The before and after. Hopefully you'll see that these buffers, they pretty much stayed the same color, whereas these two did not. Right? They changed when I added my 5 drops. Which means I don't think DI water or sodium chloride was a very good buffer, if at all. Whereas these two definitely were good buffers. They did not change pH when I added my 5 drops of acid. I treated them all the same way, buffers versus non-buffers. Our second set of test tubes, we're going to do the same thing, except instead of a strong acid, we're going to add a strong base. So I've got my samples already in there. We need to add our indicator, which is our cabbage juice. A squirt in each one. So this is repeating what we've already done. DI water, and then the sodium chloride was that. Our low pH buffer, and our high pH buffer. We know that the buffers resisted change to the hydrochloric acid. Will they also resist change to our strong base, which is sodium hydroxide? That's a strong base. This one's got this cool little dropper built right into it. Nice. Okay, let's go ahead and try this one. We're starting off on that purple color. Again, there's our DI water, and we'll add 5 drops of sodium hydroxide. 1, 2, 3, 4, 5. That's kind of pretty, isn't it? We've got that green on top. We can see it's definitely changing color. Let's go ahead and mix it. All right, boy, it's not purple anymore. It definitely changed pH. Try the salt water, same idea. 1, 2, 3, 4, 5. We see the same behavior happening, don't we? Let's go ahead and mix that. And sure enough, so water, salt water with sodium chloride, not being a very good buffer at all, not showing any kind of buffering action. Here's our low pH buffer. Will it resist? Will it change? 5 drops. 1, 2, 3, 4, 5. All right, and I don't know. I might see a little bit of color swirl at the very top. Not really. Let's go ahead and mix it. I don't know. It looks like it stayed the same color to me. And let's try our high pH buffer. Same idea. 1, 2, 3, 4, 5. All right, it started off green. Give that a mix. It's still green. So that's a great demonstration that buffers resist change when you add in either a strong acid or a strong base. They resist change in pH, whereas non-buffers, they definitely change. And actually, here's kind of a nice way to look at it. We put these side by side and keep them in the same order. This is where we added the acids. This is where we added the bases. You can see that the buffers, a little bit of difference in color when I added either an acid or I added a base, right? Add an acid or a base. But these guys, totally different between add and acid base because their pH changed a lot.